Now you guys understand you're not getting all day to do this. So. I know. I think that's what you do. I have to go back check. I don't. It's on that side. It's on that side. You mean like the last one?
Yeah. I mean,
You made it like that. I'm not. I guess it's kind of lame, but I guess.
yay! Yeah. There's what?
How you didn't guess? On your bonus question?
Oh,
Well, you got a 1 out of 50 chance. And really, you could probably narrow it down even more. I mean, the answer is not Nebraska. Iowa.
Oh, wait. Okay.
Do I have everybody's? Ross, I got yours. Say 2. So a little bit of a trick question there. Because you automatically assume that this would have to be a coastal state bordering an ocean. But it's actually Michigan.
You can't still.
What? What's what?
They don't have a.
5,000 lighthouses.
Think about Michigan. The Great Lakes. I mean, it's like the entire border of Michigan is on water except the border of Ohio, almost.
Lighthouses for sailors. Right? Like on their way home.
So they don't like crash into
So like, why are people sailing?
It's so they don't. When you say sailors, you mean people who are out in like sailboats, like
Yeah. Like fishing.
I mean they're for all kinds. They're for navigation
Yeah.
on water. The Great Lakes have a lot of boats that navigate the Great Lakes. Like, you know, it's a huge shipping lanes to go through the Great Lakes. Oh yeah. Well, just think about where's steel country? Like, where's all the steel made? And you know, in our country. There's a football team.
Yeah, Steelers.
Steelers, yeah, like Pittsburgh, like the whole like eastern side of Ohio. All that steel and all that stuff. Well, if that's going to get shipped across the country, one way to do that is go through the Great Lakes. They can put those on boats, or they can get like iron ore to make steel comes from different places. They ship it on big, huge ships across the Great Lakes into Pennsylvania and Pittsburgh. And yeah, Great Lakes have a lot of big boats. Have you ever been to any of the Great Lakes? What? They're dirty? I mean, Lake Superior's not.
Lake Erie.
Lake Erie is the one that borders Ohio, and it's. I don't think it's. I mean, it's not like crystal blue, clear water like you might see in.
There's some.
But parts of Lake, you know, the Great Lakes can be like that. Like up in Lake Superior, it's just cold. Yeah, it's just what cold. I mean, Lake Superior is freezing cold in the summertime. In the dead of August, it's like 68 degrees or something, 70 degrees. It's just pretty cold for swimming. All right, so we're going to talk about improper integrals. We're going to start our little talk about that. Improper integrals. So, what's an improper integral? It has nothing to do with like its behavior or how it acts in public. It's having to do with the bounds. Okay, there are 2 types of improper integrals. So what you're looking at there, that's the first type, or I call it type 1. We'll look at type 2s tomorrow. But this is an example of type 2 or type 1, what I call a type 1 improper integral. So what do you think makes this improper? What looks weird about it?
The infinity?
Yeah, the infinity in the bounds, okay? So if I were to ask you, like, sort of, maybe geometrically, if I were to ask you, like, say, geometrically to describe what that integral might represent geometrically, it would be an area, right? So if I think about what area that would be, 1 over x squared looks something kind of like this, right? and here's x equals 1. So if we were to describe this integral geometrically, it would be this area, right? From 1, but never stop. Okay. Everybody follow that? So the question is what do we do to compute this? Okay? Because infinity is not a number, we technically can't do this the way we would traditionally evaluate an integral. I mean, how do we traditionally evaluate an integral? We find the antiderivative, and then we plug in the two endpoints and do the math, like what you just had to do on your quiz, right? But infinity is not a number, so we can't plug in infinity. So the workaround for that is to make this a number, but have that number approach infinity. So how we do that is we traditionally use the letter B. We change this into a limit problem. And we do that. And now we just say B is a number, but we'll make B approach infinity. And we'll do a limit problem, okay? So let's go ahead and compute this and see what happens. So what's the antiderivative of 1 over x squared? I thought I heard someone say it. Ryan, did you say it? Oh, who said it? It was from this direction. Oh, Ross, what did you say? Is it 1 over x? No. Negative 1 over x. Because this is x to the negative 2, so you add 1, flip it. So negative 1 over x, and we'll evaluate this from 1 to b. And that's going to be negative 1 over b minus negative 1 over 1. Right? And now we're going to compute this limit. I guess we can do one more cleanup step here. That's negative 1 over b plus 1. So what happens as b goes to infinity? What are we left with? What happens in that first term? Right here? This is approaching 0, right? So the answer to this limit is 1. So what does that 1 mean? What does that 1 mean? Don't just get that answer and not know what it means. What does it mean? Go back to this idea of what this integral geometrically represents. What does that 1 mean? Ross, you got your hand up? You're going to say something that didn't make sense to you?
Yeah.
Oh, well, maybe it would make sense to us.
I don't want to say it.
Becca, what do you think?
Did the curve like flattens out at 1 and then just stays there?
This curve flattens out at 1? Like that? Is that true? That curve would have a horizontal asymptote of 1? In fact, I know that doesn't have a horizontal asymptote of 1. If you go back to your days with algebra 2 and pre-calculus, 1 over x squared has a horizontal asymptote of 0 because it's bottom heavy, right? In order for 1 over x squared to have a horizontal asymptote of 1, it'd have to be balanced. Remember that? So what does the 1 mean? This area is approaching 1, right? The area here is going to approach 1. All right. Now, if I stop this, instead of going integrating from 1 to infinity, I integrated from 1 to 300 million. I'm going to get something that's really close to 1, but not equal to 1. It'll be 0.9999999. Okay. Everybody cool? All right, so let's kind of define what an improper integral is, like officially, and then we'll do some examples of these type 1s. We're only going to work on type 1s today. Tomorrow, I'll make a video of type 2s. Okay? So you can watch a video tomorrow of type 2s. So an improper integral, officially, which I'm going to call type 1. Our book doesn't call these type 1. They don't call them type 1 and type 2. But... So if we have an integral of this form, a to infinity, where a is just some real number, we're going to say that this is equal to the limit as b goes to infinity of a to b okay? If this limit exists, we say that the integral converges. That's a new word, I think. Have we seen that word before? Converges? You also could say it's a convergent integral. All right. If the limit is infinite or does not exist, we say the integral, does anybody know the opposite word? I think I heard it. What did you say? Diverges, exactly. Okay. Now, one thing that this sort of has to go without saying is if you go back and think about that area, all right? If these integrals represent some sort of area, right? We're all in agreement with that. They're representing some area. The only way that this integral, the only way that this area would have a prayer at approaching something and not get bigger and bigger and bigger. What has to be true about the function? And this is kind of goes back to what Becca brought up, unintentional. What has to be true about this function for this integral to even have a prayer at converging? It has a horizontal asymptote, but more specifically, the horizontal asymptote would have to be 0. Okay? Because think about this for a second. If it had a horizontal asymptote of 1, like Becca suggested a second ago, so there's 1, and you're looking at the area from 1 to infinity, how could that possibly approach something? It's just going to keep getting bigger and bigger and bigger and bigger. Like the curve has to be getting smaller and smaller and smaller. Okay? So we'll add this little caveat here. We'll say it right here. F of x has to approach 0 as x approaches infinity. Okay? So a type 1 integral is when you have infinities in the bounds. Okay? Now, it doesn't have to be positive infinity. This could also be considered a type 1. So I want to just throw that up there. So like we could integrate from negative infinity up to some other number. And guess how you do that? How do you think you do this? You do it the exact same way, except you just do it as b goes to negative infinity instead of positive infinity. But the way we go about doing it is the exact same. Okay? And you could even have, and we'll do an example of this, you could have infinites on both. And we'll do an example of that in a second. Okay, so all three of these would be considered type 1s. All right, so you want to do more problems? Another couple of examples? Got about 10 minutes. What's hard about this? What about improper integrals is going to be difficult for you? There's two things that you're going to have trouble with. What are they? First thing, finding the antiderivatives. The second thing, evaluating those limits. Like, you got to be good at doing those limits. You know what might come up when we do these improper integrals? L'Hopital's rule. Remember that? L'Hopital. Oh yeah, we learned that. I think we learned it while we were hybrid. The good old days of hybrid. Those were not the good old days. Those were the terrible days. All right, let's try this one. Woo. 1. I like 1 as my lower bound. All right, so here we go. Ready? So that's improper, right? So we'll change it into a limit problem. Can you find the antiderivative? What is it? Natural log of x, baby. So I got the natural log of b minus the natural log of 1. Yes? What's the natural log of 1? So, you guys didn't jump on that like as quickly as I would have liked you to. Okay, what happens to the natural log of b as b goes to infinity? It's kind of helpful to know. If you don't know off the top of your head, you're going to know probably after today, because you'll do it so many times. Think about the graph of the natural log function. What does it do? The natural log function. What does the natural log function do? The natural log function looks like this. It just keeps increasing. It increases very slowly, but it keeps increasing. So what happens if I take the limit of the natural log of b as b goes to infinity? What's going to happen to this? It's going to keep getting bigger and bigger and bigger, but slowly, but it's going to keep getting bigger and bigger and bigger. So this is infinite. So what do we say about this improper integral? He's a diverger. Okay? Now, guys, you sort of have to like wrap your brain around this, because this is crazy talk. I mean, this is almost black magic here. Like, a second ago, I gave you 1 over x squared, looks like this. Okay? This integral from 1 to infinity on 1 over x squared was approaching 1. And then a very similar graph, okay? 1 over x looks like this. I'll draw it in a different color. It looks like this. Okay? And if I start here at 1 and go to infinity and find that area is approaching infinity. There's a big honking difference between 1 and infinity. Right? And that's kind of whack. Now down the road, we'll see when we get into fourth quarter, we'll see kind of why that happens. But it really has to do with how fast it's approaching 0. The 1 over x. 1 over x squared is approaching 0 much faster than 1 over x is. 1 over x squared is beating it to the, to 0, so to speak. All right? So that's crazy town, I know. This integral is divergent, 1 over x squared was convergent. Kind of whack. Let's do another one. Oh, let's do this one. Because you're going to like the answer to this. So this is still type 1, but now it's a weirdo because it has infinity on both. Right? So here's what we're going to do. We're going to break this up into 2 improper integrals. Now, where might be a good place to break this up? We're going to go from negative infinity to infinity. Where might be a good place to break it up in the middle? 0. Now, 0 is technically not in the middle of negative infinity to infinity because there is no middle. But when we picture a number line, 0 is kind of in the middle, right? So let's break it up and we'll say, okay, kids, this is going to equal the integral from negative infinity to 0 of 1 over x, 1 plus x squared, plus the integral from 0 to infinity. Yeah. And then we'll turn this into a limit problem. The limit as b goes to negative infinity of b to 0 of 1 over 1 plus x squared. And then the limit as b goes to positive infinity of 0 to b of 1 over 1 plus x squared. So I just broke it up into 2 separate type 1s. Okay? Does anybody know the antiderivative of 1 over 1 plus x squared? If you don't know it, you would have to do a trig sum. But what function has a derivative that's equal to 1 over 1 plus x squared? It's not tangent, but it's close. Inverse tangent. And that's probably what you meant, Maddie, when you said that. Could you do partial fractions there? You wouldn't want to do partial fractions there because there's only one factor. You would only do partial fractions if you have multiple factors in the denominator. And we'll do this one here. Okay, so here we go. We're going to do the limit as b goes to negative infinity of inverse tangent of b minus inverse tangent of 0. And then the limit as b goes to positive infinity of inverse tangent of b minus inverse tangent of 0. What's the inverse tangent of 0? What angle has a tangent that's equal to 0? 0. Okay, so this is 0. So that one's 0 too. What's the inverse tangent of b as b goes to negative infinity? So let's think about it this way. What angle is tangent undefined at? What angle is tangent negative and undefined? Where is it approaching infinity? Negative infinity. I heard someone say it, I thought. 3 pi over 2. But let's give the coterminal of that, because technically speaking, when we're talking about inverse tangent, we're only giving answers between negative pi over 2 and pi over 2. Otherwise, inverse tangent wouldn't be a function. So what's coterminal with 3 pi over 2? That's between negative pi over 2 and pi over 2. Negative pi over 2. Okay? Oh, wait. Oh, guys, I just noticed something. What's wrong here? These are reversed. That would have been problematic. So the answer here is negative pi over 2. Plus, what about over here? What's the inverse tangent of b as b approaches positive infinity? Where's the tangent undefined and positive? Pi over 2. So when I do this arithmetic here, I get pi over 2 plus pi over 2, which is pi. Okay? So this integral converges. It's approaching pi. 1 over 1 plus x squared, in case, I mean, you probably just don't know off the top of your head what it looks like, but it looks like this. It kind of looks like the normal curve. If you're in stats, it's not, but it looks like it. So the area under this curve is actually approaching pi. Okay. I had one more example to do, but I don't think I'm going to get to it. So I'm going to give you some problems. I'll post these in Google Classroom of just practicing some type 1s if you're going to want to do these tonight. And guess what? You might have to integrate by parts. Yeah. You should already know those. I don't know that I would say, do we start? Yes, you started. Oh, if you're a junior and you wanted me to sign your little thing here. Oh, yeah, all right.
I don't know yet.
Any class is not going to take Calc 3.
This is too hard for me. All right.
Oh, any class. This is not too hard.
Real world application. Or is this one just
Are you serious?
I don't have other math. I pull my couch from my college. I don't know. Can I ask you to change my quiz to 65?
I should have got my calculator.
Wait, it's error.
What? Why did also, I looked at this and that's
What are you doing?
They're all like this. Oh my God. But I have to change my quiz. Actually, like, I just see a bunch of zero. I need to change that. I'm gonna go. So I actually simplified natural log of 0 to 0. Is there any way I can change that to keep it at 0?
You mean on this?
Yeah.
You shouldn't have gotten natural log of
I don't
0.
know why.
Where would you have gotten natural log of 0?
It was like 5. Oh my God. I put 5 minus 5. Oh my God. I could never get a perfect score in quiz. I just can't do it.
Yours might help. Gave me the wrong.
We've never done one with like the bounds, like that.
You mean you never did a definite interval? Like
No, I
ever?
think I've done that. We just hadn't done it for the
Is
part.
this, you picked your answer based off of this?
Yes, because there's
Well, this is lighthouses of the East Coast.
Is it
Is it Michigan on the East Coast? No. Oh, gosh.
Why are you not checking more than you
Because I did it wrong. Like, I probably didn't vote wrong. I don't really remember why. I remember that I'm not technically voting. Because I did it wrong.
Yeah, I mean, you can. That's, man, this sucks though. You're not gonna get credit for all this.
I'm gonna take so many more classes. I'm not gonna.
What are you,
Engineering.
This sucks though, is you're not gonna have to take that many math classes. You really have to take one more, maybe two, and you'll be done after about 3. I mean, you're gonna go and it's gonna be a joke.
Karen, how are you?
Good, how are you?
Good, I mean, better if there's coffee left there.
I'm not.
I don't remember what your issue was.
You don't know how bad this is. How am I gonna make it through the day?
I kind of can remember talking to you about that, like through a Zoom.
Yeah.
Yeah.
But I can still.
Oh, yeah. It would be a travesty if you would not. Yeah.
Oh, yeah.
Like, you know, when that's a bit for people, man.
Oh. Quiz.
Whoa, yeah, gonna show how smart they are. Woohoo!
Oh.
Yep. Good luck. Oh, good skill. Take the coffee, there is none.
Yeah, we're out. I don't know if we should make more. This coffee's good. I gotta think of a bonus question for you guys. Maybe the same one we last period. Okay, here's your bonus question. The tallest mountain in the world is Mount Everest. What mountain range is that a part of? You don't have to spell it correctly.
can we just write like on here? Like, I have it down.
You could, but that's not actually right. That's actually in the United States.
That's fine.
Mount Everest is not in the United States. Did you guys not know that?
No.
I'm horrible with geography.
Yes,
Oh,
I
my
know.
word.
It's like somewhere far away.
It borders 2 countries, Nepal and something else. China, maybe? No, it's Bless you, my son. It doesn't have to be that. Good enough. Yeah. I mean, I don't know. I'm not saying those are right. but-
Yeah, just is that simplification.
I don't want you to spend 4 hours running that one wall. Yeah, that's. Are you done?
Alright.
It is.
Okay. I didn't know.
Well done. You just guessed that?
No,
You
I
pulled that out of
didn't
your
guess.
butt?
No, I didn't know if it was like
Oh.
right.
So you use sort of an educated guess. Yep. I have no idea how to spell it. I feel like Carrie's spelling might be closer.
Yeah, I'm not sure.
Oh, I know.
I think yours is closer than Samuel's.
Oh, mine's not.
Is mine right?
Yeah, that's a pretty big difference. Like when your first answer.
What?
I just put.
I mean, It was between the two. And I went for one, and
I should have told you. Yeah, who's done? Who else is done? You gotta be finishing up soon. This shouldn't be an all-day affair here.
that's crazy. That's actually first. This is I didn't say we were having a good day.
Huh?
Yeah. I'm just a random guess.
Oh, the test.
Oh,
You actually gave me the name of a mountain in Africa.
oh well, it's an answer.
Made popular by a song by Toto. So, you. But she'll be over. She didn't know who it was.
Now I got you. Think about it.
What period is this period in?
24.
What period is this period? Yeah, period ends. This period.
This is not bad. What?
Are you familiar with like the 7 bridges problem?
Yes.
It's like not solvable, correct?
I don't know that it was ever solved. That problem actually sort of morphed into an entire branch of mathematics called topology. Oh, sorry, you're right. It is graph theory.
Topology is like the shape,
Yeah.
like
Sorry.
donuts, and you're talking about the same thing.
Yeah.
I know.
7 bridges of conics.
Seven bridges problem? I was gonna say no to either.
I also heard of the 7 bridges row equal sum.
So like, it's theoretically unsolvable, right? Like that's the thing about it.
Yeah, there's lots of unsolved problems.
So like, no, it's not like it's unsolvable. There's no way to like get it correct. Like, you can't do it, right?
Right, but then there's also the problem of proving that that's unsolvable.
But like, we're following it with someone said,
Pretty good.
that someone followed it, and it's like, no, they didn't.
You're not. So you and I have an email. You're not enrolled in this state right now. Okay, so yeah, your plan is totally works.
Yeah.
In fact, well, we can talk. Hang on, I have options. Okay, friends, it's time for us to talk about improper integrals. Okay, oh, the answer to your bonus question was the Himalayan.
Oh my God.
How did I think if that was
India, yeah. I said China, I knew that was wrong.
It's because
India and Nepal.
you can remember because it's formed by the Indians like crashing into the grazing.
The Himalayas.
I thought that was even a thing.
I think it's Himalayas, not Himalayans.
I think
Himalayans would be
I think Himalayans would be like people.
people, yeah. I'll take that. Jeopardy wouldn't take it, but I'll take it. So this, my friends, is an example of an improper integral. Okay, an improper integral doesn't mean that it belches at the table. Okay, it has to do with the bounds. Okay, what makes it improper? What do you notice about these bounds? One of them is infinity, right? And that's what makes this improper, okay? There are 2 types of improper integrals. We're going to talk about what I call type 1s today. And then I'll make a video for tomorrow that talks about type 2s. Type 1s are improper or integrals that have infinite or infinities in their bounds, okay? So, you know, normally for an integral, you would just like find the antiderivative and then plug in the bounds, right? But that really is only valid when the bounds are numbers. And much to your dismay, infinity is not a number. Okay, infinity is not a number. So I can't just plug in infinity here. So the workaround, it's an easy workaround. We just pretend there's a number up there and then make that number approach infinity. Okay, so we turn this problem into a limit problem. All right, now before we go about solving this, I think it might be worth exploring or talking about, discussing what geometrically Like what geometrically does this integral represent? Well, it represents some area, right? If I think about this graph of 1 over x squared, 1 over x squared kind of looks like that. Okay? Here's x equals 1. So what area is this representing? Well, it's the area from 1 forever. Starting here and going forever. Right? That make sense? So maybe let's compute this and see what happens. And then we'll give you a formal definition of like what an improper integral is. So if I compute this, the antiderivative of 1 over x squared, do we know that? It's negative 1 over x. And I'm going to evaluate that from 1 to b. So now we're going to do the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. And then I've got the limit as b goes to infinity of negative 1 over b plus 1 over 1 or 1. So what is that limit as b goes to infinity? What happens to this part right here as b goes to infinity? That's going to 0. So this thing right here, the total answer is 1. Now what does that 1 mean? I mean, who cares if we can get an answer if we don't know what it means? What does that 1 mean? Don't make this harder than it is. Alex, what do you think?
From 1 to infinity, the area underneath the graph just equals 1.
Normally, I would say that's okay. I would take that. But I think you can make that stronger. Does the area equal 1? Because remember, go back to this idea that infinity is not a number. Aaron, what do you think?
The area approaches 1.
Yeah, this area is going to approach 1. You see the distinction there? Alex, why I'm being kind of a pain. This area approaches 1. As we approach it, as b goes to infinity, right? Now, if you said equal 1, I'm not going to flip my head off. Kind of impressive if I could do that any bigger. Okay? So let's give like now a formal definition of what a type 1 improper integral is. So we're going to say when we have an infinite in bounds like this, we compute this. And typically we just use the letter b. I don't know why we use b. We just do. If you want to use t, use t. That's what our book does. It's the first book I've ever seen use t for their improper integrals, but knock yourself out. Okay? So if this limit exists, we say that the integral converges. If the limit does not exist or is infinite, we say the integral. Anybody know the opposite word? Diverges. Where'd you hear that word? You say the integral diverges. Okay? So this first example that we just did, that improper integral converges. And it converges to 1. Converges to 1 is like saying it approaches 1. Okay? Now, I don't know why kids oftentimes will say that converges at 1. I don't know why they say at there. It should be to 1.
Like or whatever you would say converges at, and that's probably going to
Yeah.
converges. If you're pretty outside.
If you want to use an adjective form of the word is convergent and divergent. We say that integral is convergent or divergent, but then that mixes it up with a bad teen series. So,
Whoa.
did you read those books?
No.
Did you see the movies?
Yes.
I saw Divergent. I remember the first time I saw that book. This kid had that book in my class. And I thought it was a book about math. I had no idea. I didn't even know there was a second one. I mean, I think I watched Divergent with my kids like many years ago. Okay, so let's go back to our example. Okay, because there's one thing that we sort of forgot that's really important, and I intentionally forgot it because I wanted to emphasize it. It's really important to this definition. Okay? So go back to this example, this picture. Something had to be true about this function in order for it to even have a prayer. Think about that graph right there. In order for that graph to have a prayer at converging, and we were going to integrate from 1 to infinity, what has to be true about the graph? For example, if I gave you this graph, and said, okay, integrate that function from 1 to infinity, we wouldn't even have to do anything. What would the answer be? Infinity. I mean, if this graph is increasing, like, we're finding area, I mean, the area is just going to keep getting bigger and bigger and bigger, right? I mean, that's stupid. So what's got to be true about our function? It's got to have a 0 as its horizontal asymptote. Okay, the function needs to be approaching 0, or otherwise this is a waste of time. Okay, so we'll say up here, f of x approaches 0 as x approaches infinity. Okay. Now, this is not the only example of a type 1. A type 1 could also be this. Instead of having infinity, you could have negative infinity as your bound. Okay, that's also considered a type 1. And guess what? How do you do that? The exact same way. You just make b go to negative infinity instead of positive infinity. And on top of that, you could have infinities in both bounds. Right? And you'll do the same thing. In fact, we're going to do an example of that in a second. Right? So infinity in the bounds could be in the upper bound, the lower bound, or both. They're all improper, and they're all like what I call type 1s. All right?
So it's not a standard phrase.
Type 1, no. That's a mitter phrase. All right, so let's do another example here, friends, of a type 1. I like 1 as my bound. Okay, so while you're writing down the example, I'll tell you where you're going to have trouble with this. Finding the antiderivatives and computing the limits. Okay, computing the limits might give you some trouble. You might have to use L'Hopital's rule. Remember that? We learned it back when we were hybrid. There's a nice song that goes along with it. L'Hopital, every now and then I get a little bit of trouble when I'm taking a name. That sounds familiar. You guys are looking at me like I have 3 heads. All right, so here we go. So we're going to recognize that this is improper. We're going to change this to a limit problem. And then we're going to say, oh, okay. Find the antiderivative. What's the antiderivative of 1 over x? That's an easy one. It's the natural log of x, and evaluate that from 1 to b. So I've got the limit as b goes to infinity of natural log of b minus the natural log of 1. The natural log of 1 is... You guys are not answering that as fast as I would like you to. 0. Right? So now I've got limit as b goes to infinity of the natural log of b. What's the answer to that? Maybe you just don't know that off the top of your head. You probably will after today. What happens to the natural log function as what you're logging gets bigger? If you're not sure, think about what the graph of the natural log function looks like. Looks like that. So what happens as x gets bigger and bigger and bigger? What happens to the natural log? It gets bigger and bigger and bigger. The natural log function is a function that continues to increase very slowly. I mean, the rate of change of natural log is 1 over whatever you're logging. So it's not increasing very fast. But it's still increasing. So what's the answer to this limit problem? Infinity. Okay? So friends, here's 1 over x. If I find that area from 1 to infinity, it's approaching infinity. This integral diverges. Now, people, this should rack your brain slightly. Okay? Because if you were paying attention 5 minutes ago, and we did this example here, which a minute ago, we did the function 1 over x squared, which looks like this. Okay? This pink area, from 1 to infinity, was approaching 1. This area, from 1 to infinity, under the other curve, is approaching infinity. There's a big difference between those two, right? And we'll learn in 4th quarter sort of why this happens, but it has to do everything with how fast those things are approaching 0. 1 over x just isn't fast enough. It doesn't approach 0 fast enough to make that area approach something finite. Okay? That should be mind-blowing. Is it? I mean, we got an answer of 1 before, and we just changed the graph slightly, and now we're getting an answer of infinity, and it essentially looks like the same area. Okay? Sort of, that bothers me a little bit. Why don't it bothers me? Maybe one time it bothered me, now it fascinates me. It's like my bread and butter now. So it puts food on the table, you know? All right, let's do another problem. You ready? You're going to like this answer. You're not going to like the problem so much, but you're going to like the answer. So this is a type 2, right? That has bounds on, upper and lower bounds of infinity. Okay, now I'll go ahead and show you, just because I can do it real quickly. The graph of 1 over 1 plus x squared looks like that. So we're talking about this area under this whole thing there. Forever. Right? So how do we deal with one that has infinities in the upper and lower bounds? Okay? Pick a number and then split it into 2. What do I mean by that? Well, what number might be sort of a good number to break this up at? 0, 4 would work. But there's symmetry there, so 0 probably just feels better. But 4 would work. You just got to pick somewhere, you got to pick a number to break it up. Okay? So I'm going to break this up, and I'm going to say this answer is equal to this. Okay? And you might even make the argument that, hey, I could use some symmetry there and say, I'm just going to break this into 1 and double my answer. Do you guys see the symmetry of the graph? I mean, I could just go from 0 to infinity and double the answer. Does everybody see that? And that's totally legit. In fact, let's just do that since we're kind of getting short on time. So let's just say that's going to equal 2 times this. Now, normally speaking, if that symmetry is not there, you might have to do 2 separate problems. Okay? So let's go, that's 2 times the limit as b goes to infinity of the integral from 0 to b of 1 over 1 plus x squared. So what's the antiderivative of 1 over 1 plus x squared? If you don't know it off the top of your head, you should, probably. You could do a trig sum to find it. What is it? Do you know it, Gavin? It's inverse tangent. I thought I heard you mumbling in it. It's hard to hear your guys' mumblings with masks. So inverse tangent of x, and we're going to evaluate that from 0 to b? So that's the inverse tangent of b minus the inverse tangent of 0. I'm just going to leave it on the, I don't know where you would put the 2. You know what I mean? You could stick the 2 there in front of inverse tangent. It's not 2b.
Shouldn't it be 2 limit of the difference going to be an arctangent of b minus 2 times the arctangent of 0?
No, because it's, I'm thinking of it like that.
Okay.
All right, so what is the inverse tangent of 0? Can we do that first? What angle has a tangent of 0? What angle has a tangent of 0? 0. Now let's do the inverse tangent of b as b goes to infinity. So in order to answer this question, you really have to think about where is the tangent undefined? Where is the tangent approaching infinity? Positive infinity. Where? 90. Or in radians, which is what we do math in. pi over 2. Okay? So this limit, as b goes to infinity, the inverse tangent of p is pi over 2. So the answer to this problem is 2 times pi over 2, or pi. Told you would like that answer. What does that number mean? The area under this curve here, from negative infinity to infinity, is approaching pi. Does everybody understand why the inverse tangent of infinity is pi over 2? I mean, in the tangent world, in the secant world, in the cosecant world, the cotangent world, undefined really means it was approaching infinity. It was huge, had a vertical asymptote, right? In fact, in your world, more often than not, when you hear the word undefined, it really is meaning infinite. Think about that. Oh, vertical lines have undefined slope. Didn't somebody tell you that sometime in 8th grade or something? But realistically, a vertical line, what kind of slope does it have? Infinite slope, right? Oh, you can't divide by 0. It's undefined. Well, once you learn calculus, you kind of can divide by 0. When you divide by 0, you're approaching infinity, right? So this is another example of a type 1. I'm going to give you some in the Google tonight, where you have to do some type 1s. Hey, you might have to integrate by parts. Okay, you might have to integrate by parts. Then tomorrow, I'm going to make a video of type 2s and give you some of those. And then we'll talk about all those on Thursday. What? Your test is still on Monday.
Oh,
Yeah.
That's gonna be on.
This probably will be on it, but probably only like one problem.
So it's just.
And I'll give you some review problems for the test, just some, more practice to get ready. I'll give those to you on Thursday. I may even put those out tomorrow, just for those people who want to get a heads up, or a leg up. I mean, the test is a big deal, dudes. Like, big deal. So, integration by parts, trig subs, partial fractions, U subs, and integration with Calc. So, please be with you. Little geometric series joke.
What do you take after you take out differential equations?
After partial differential equations?
Yeah.
I mean, if you're taking classes beyond partial differential equations, then you're really, you're a math major. I mean, you're taking topology.